Hello students. So our today's topic is magnetism and matter, NCERT section 5.3, example 5.3. So let's begin. This is disclaimer. So learning objectives. After this lecture you will be able to understand how Gauss law for magnetism closed integral B dot dA equal to 0 show that there are no magnetic monopoles and magnetic field lines must form closed loops with no beginning or end. So the index of topics that we are going to discuss today is NCERT section 5.3, magnetism and Gauss law, and example 5.3. So let's begin with our topic. That is magnetism and Gauss law. Okay, so firstly, to discuss about Gauss law, we will discuss about the magnetic flux. Okay, so this is a diagram, this is a figure showing magnetic field lines passing through a surface. Okay, that is B magnetic field, and it number of magnetic field lines are passing through this area A. Okay, so the magnetic field due to this magnetic field lines is shown as this by red vector. This is B vector, and this is area. This is some surface of area A, and this is the area vector. Area vector, or we can say normal vector. And area vector or normal vector is always perpendicular to the surface of the given body. Okay, so this is the surface. It is always perpendicular to the plane of surface, area vector. Okay, so the angle theta we are taking here in the magnetic flux. Okay, we have studied about electric flux also. So magnetic flux is analogous to that. Okay, so in electric flux we discuss about the number of electric field lines passing through a given surface normally. Okay, now we are taking magnetic field lines, and theta is the angle between the direction of magnetic field and area vector. Okay, this theta is not between magnetic field and this plane of surface. It is angle between the area vector that is perpendicular to this plane of surface and magnetic field. Okay, so magnetic flux through any surface is defined as the amount of magnetic field lines passing through that surface normally. Now you can you have to give your attention to this normally. What is normally means? It means that magnetic field, the component of magnetic field that is along this area vector will be considered. Okay, so magnetic flux, the definition, according to definition we will come to mathematical part. So definition is showing that amount of magnetic field lines that are passing through this surface normally. Okay, so this magnetic field is not normal to this surface. Okay, so for normal component we have to resolve it into components. So it will become B cos theta, and the component that along the surface will be B sin theta. Okay, so we will take the component that is normal, that is perpendicular to this surface or along this area vector. Okay, so phi is equal to, what is phi? Magnetic flux. So phi is used for magnetic flux, which is equal to component of magnetic field normal to the plane of surface. Okay, component of magnetic field that is normal to the plane of surface into area of the surface. So it will result in phi is equal to B cos theta. So the component that is normal to this surface will be B cos theta into the area of this surface. What is the area of this surface? A. So it will become BA cos theta. Okay, so BA cos theta is, if we want to write it in vector form, so it will result in phi equal to B vector dot A vector. We know that the dot product of two vectors result in a scalar quantity. So this magnetic flux is a scalar quantity. Okay, it is the dot product of magnetic field and area vector. Got it? So it will result in BA cos theta. Or you can take it as both. You can modify the definition also. You can write that magnetic field, we will not change the direction of magnetic field, but we will take the area vector, then we can take the component of this area vector along the magnetic field. We can solve, we can derive the expression for this magnetic flux in two ways. Either we can take the component of magnetic field in the direction of area vector, and that is perpendicular to the plane of surface, or we can take the component of this area vector in the direction of magnetic field. In both cases, it will result in BA cos theta. Okay, in this case, it will result in B cos theta into A. Okay, in second case, if we are taking component of A along the B, it will result in B A cos theta. Okay, in both cases, it will result in BA cos theta and eventually B vector dot A vector. So this is the formula for magnetic flux. In electrostatic, we have studied that electric flux was E vector dot A vector. Okay, so it is analogous to that, where theta is the angle between the area vector and magnetic field. So what is the Gauss law in electrostatic? Okay, Gauss law in electrostatic you have studied already. Okay, so there is a quick recap. So from chapter electric charges and fields, we know that surface integral means closed integral of the electric field over a closed surface is Q by epsilon naught. Okay, so surface closed integral E dot ds. ds is surface area of small area element. Okay, so closed integral E dot ds is equal to Q by epsilon naught. This Gauss law we have studied in the electrostatics. Okay, so surface integral of the electric field over a closed surface is Q by epsilon naught, where Q is the net charge enclosed by the surface. Mathematically, Gauss law in electrostatic is defined as closed integral E dot ds vector, E vector dot ds vector equal to Q by epsilon naught. What is this ds vector? This is area vector of small area element we have taken, where E is the electric field and ds is the area vector of very small area element. Now, electric flux through a closed surface. So what is the electric flux through a closed surface? Figure 5.2 C electric dipole. This is a diagram for electric dipole. Now in figure 5.2 C, we can see that for a closed surface represented by 1. So what is this one? This one. This surface 1. Okay. The number of lines leaving the surface is equal to the number of lines entering it. If this is a closed surface, okay, in 2D it is represented by this loop. Okay, but actually it is not loop. It is closed surface. If you can imagine it, this surface in the form of a 3D. So it is a irregular closed surface. Okay, so like there is a football. Football is a closed surface, but it is regular. If same type of surface is there, but it is not completely spherical, it is some irregular shape. So that is that surface first. So that is closed surface represented by 1. So number of lines that is entering this closed surface is equal to the number of field lines exiting this closed surface for this first surface. Okay, the number of line leaving the surface is equal to the number of lines entering it. So hence net flux through surface 1. Net flux through surface 1 is number of lines entering means inward flux, and number of lines exiting from that surface is outward flux. So inward flux is equal to outward flux. So net flux through surface 1 is 0 here. 0 net flux is consistent with the fact that no net charge is enclosed. If net flux through any surface, net electric flux through any surface is 0, that means that there is no net charge enclosed by that surface. This is the conclusion for Gauss law in electrostatic, that if there is no charge enclosed in the closed surface, then it means net flux through that surface will be 0. Okay, so we have calculated, we have seen that net flux through that surface 1 is 0. That means no net charge is enclosed by this surface 1. Okay, However, in the same figure 5.2c, you can see the diagram closed surface 2. This is the closed surface 2. This. Follow the cursor. This is the closed surface 2. This is not a loop. Okay, it is represented in the form of loop, but actually it is surface. Okay, so for this closed surface, for this ellipsoid, elliptical closed surface, okay, there is a net outward flux because there is a positive charge enclosed. This is a positive charge. Okay, this is a positive charge. So this surface is enclosing a positive charge. Okay, so there are no electric field lines that are entering this surface. You can see in the diagram, for this second surface, there are no electric field lines that are entering. Only electric field lines are exiting from here also. It means there is only outward flux. Inward flux is 0. Okay, inward flux is not there. This surface is enclosing a charge, due to which charge is positive charge. So due to positive charge, electric field lines are in the form of radially outwards. Okay, so only outward flux is there. So however, in the same figure for the closed surface 2, there is a net outward flux. Since it does include a net positive charge, because it is enclosing a positive charge, due to which there is only outward flux, no inward flux. No electric field line is entering that surface, only exiting. Got it? Similar concept we are going to use for Gauss law in magnetism. Okay. So Gauss law for magnetism. Now figure 5.2a. So this figure and this figure, pattern of magnetic field lines are same, because this is the bar magnet, this is the solenoid. So magnetic field line pattern for both bar magnet and solenoid is similar. We have discussed in our previous lecture. Okay, so what we are going to see here, there are also first surface and second surface in both the diagrams. Okay, magnetic field lines are continuous and form closed loops. Okay, that difference we have discussed in our previous lectures, that in case of electrostatic fields are non-continuous. They don't form closed loops. They originate from positive charge and end on negative charge. Got it? But magnetic field lines originate from, we cannot fix the point, because for a bar magnet, outside the magnet, they are originating from north and entering the south. But inside the magnet, they are originating from south and entering the north. They are forming closed loop. We cannot fix the point from which they are originating. Okay, so there is no point of there is no point from where they are originating. Okay, there are no sources and sinks. That means there is no source from which they are originating, and there is no sink at which point they are ending. Okay, so magnetic field lines form closed loop and continuous. Examine the Gaussian surface represented by 1 and 2 in figure 5.2a and 5.2b. Okay, in both figures you can examine two surfaces, 1 and 2. Okay, they are Gaussian surfaces. So both cases visually demonstrate that the number of magnetic field lines leaving the surface is equal to number of lines entering it. Okay, now you can see in first case, in electrostatics, for first diagram, net flux was 0. For magnetism, for Gauss law for magnetism, magnetic flux through this surface 1 is also 0, because net magnetic field lines entering the surface is equal to the net magnetic field lines exiting this surface. Okay, so net magnetic flux through this first surface is 0. Okay, now in previous case, for electric flux, we have seen from second surface was enclosing positive charge. Okay, due to which there was only net outward flux. But in magnetism, you can see there are we cannot say that magnetic field lines are originating from North Pole. No, because inside the bar magnet or inside the solenoid, also magnetic field lines existing from south to north. Okay, so in this surface, magnetic field lines are entering from one side and exiting from other side. Okay, we cannot say also that this surface is enclosing only North Pole. No, because monopoles do not exist. Okay, if it is enclosing some part of the magnet or some part of the solenoid, it means this part is north and the other part is south, behaving as south. Okay, such that magnetic field lines is entering from this side and exiting from this side. Okay, there is inward flux also, there is outward flux also through this surface. But in electrostatics, in electric flux, there was positive charge. Due to positive charge, isolated charges exist. Due to that positive charge, only outward electric field lines were there. But due to this North Pole, because magnetic field lines are closed loops, they are not originating from North Pole. They have no sources and sinks. Okay, so magnetic field lines are entering from one side like this and exiting from other side. So for both surface 1 and 2, magnetic field lines leaving the surface is equal to the number of lines entering it. Okay, so the net flux is 0 for both the surfaces. Understood this thing? So magnetic flux for a closed surface is 0 for any type of surface. Okay. Therefore, in magnetism, monopoles do not exist. Okay, and magnetic field lines always form closed loops. This is clear. The monopoles do not exist and they form closed loop. These two concepts are vice versa. Okay, we can say magnetic field lines form closed loop, that's why monopoles do not exist. Or we can say monopoles do not exist, that's why we can say magnetic field lines don't form closed loops. Okay, this is understood, that if we can place an isolated charge in a closed surface, due to which if the charge is positive, there will be outward flux. If charge is negative, there will be inward flux. So net flux is there. Net flux is not 0. But we cannot place only one pole inside the closed surface. We cannot place the North Pole alone, or we cannot place the South Pole alone. Okay, if we are placing any pole, then other pole also exists. If we are cutting the magnet, if we are thinking that after cutting the magnet we can place the only North Pole, no. There will be bar magnet again, having both North Pole and South Pole, but reduced magnetic field. Due to North Pole, there will be outward flux, and due to South Pole there will be inward flux, because loop is forming. Okay, so number of field lines exiting the surface will be equal to number of field lines entering the surface due to South Pole. So for any closed surface, magnetic flux will be 0. Net magnetic flux will be 0. So the number of since the magnetic field form a closed loops, if we take a closed surface in magnetic field, the number of magnetic lines entering this closed surface is equal to that of leaving this surface. As a result, net magnetic flux through any closed surface is 0. This is the final result. Mathematically, it is represented by closed integral b vector dot ds vector equal to 0. Okay, so closed integral of b dot ds will be 0. Now derivation for Gauss law in magnetism. Now we will prove it through derivation. So this is the figure 5.5. You can see there is a surface, closed surface. On closed surface, we are taking a small area element, that is delta S. Okay, so area vector due to this delta S will be n cap. This is the area vector, which is perpendicular to this delta S. Okay, perpendicular to the plane of this delta S. And this is the direction of magnetic field line. And the theta is the angle between this area vector and this direction of magnetic field line. Okay, this is the figure 5.5. Consider a small area vector element delta S of a closed surface S as in the figure 5.5. Okay, you have to the surface of this whole surface. This is some closed surface. The surface area of this whole closed surface is S. So we are taking a very small area vector from this whole surface, that is delta S. Magnetic flux through this delta S defined as delta phi b. This is magnetic flux. Delta sign is there because we are calculating it for small area element delta S. Okay, not for whole surface. Initially we are calculating because surface is irregular. Surface is not regular. We cannot determine the surface area. We can only determine the surface area by using integration. Okay, so we have to take the small element over which surface is continuous, regular. Okay, so magnetic flux delta S is defined as delta phi b equal to b dot delta S. That bold sign represent the vector. Either vector we can either write it as by putting vector sign over it, or we can write it as bold font. Okay, so it will result in vector sign. So b vector dot delta S vector. This is the formula we have seen in the first slide. Okay, so this is the magnetic flux through this small area element delta S, where b is magnetic field at delta S. Divide S. So what is S? The whole surface area. Divide S into many small area elements. So we have to divide this whole surface area into small surface area elements delta S. Okay, and calculate the individual flux through each. So we have to calculate the individual flux through each. Why we are calculating the individual flux? Why we are not calculating the flux at once by considering whole surface? Because the surface is irregular. This n vector will be different for different element. Okay, for we can say for this here, if we are taking delta S here, the direction of this n vector will be somewhere else, not in this direction always, because the surface is irregular. This n vector is always perpendicular to the surface. Okay, so surface is irregular, so it cannot be same for all the small elements. Its direction will vary upon the small element, the orientation of these small elements. Okay, so angle will change for each small element. Okay, so flux will change for each small element. Got it? So we have to calculate the individual flux through these small elements. Then we are going to integrate it. Okay, so divide S into many small area elements and calculate the individual flux through each. Then the net flux phi b is, net flux we can calculate by summation of delta phi b. Delta phi b is small magnetic flux for a small element delta S. Okay, so for many small element delta S, we are going to calculate the individual flux delta phi b for all the elements. So net flux through the surface phi b will be equal to summation of all small elements over delta phi b. Okay, which is equal to summation of all. What is delta phi b? B dot delta S. Okay, B dot delta S is the small magnetic flux through small area vector, or we are doing summation for whole surface, which is equal to 0. That we have already seen that magnetic flux through any closed surface will be 0. Okay, any type of closed surface, whether it is irregular, whether it is regular. If this is closed, then magnetic flux through that surface, closed surface, will be 0 always. So mark it as 5.6 equation, where all stands for all area elements delta S. Compare this with the Gauss law of electrostatics. Okay, so by comparing this result with the Gauss law for electrostatic, the flux through a closed surface. In electrostatic, the flux through a closed surface is given by summation S E dot ds. In the electrostatic, that was the formula, and that was not equal to 0. That was equal to Q by epsilon naught. It can be 0 when Q enclosed is 0. When closed surface is not enclosing any charge, then E dot delta S will be equal to 0. Close integral E dot delta S is equal to 0. But it will result in Q by epsilon naught. But in magnetism, it is always 0. Okay, now why we are not integrating it, we are taking summation sign, because delta S is significantly large. It is not very small. To get the integration, we have to consider this delta S very small, negligibly small, infinitesimally small. Okay, very small element, for which then we will convert this summation sign into close integral sign, and we'll take this delta S will be equal to, delta S will tends to be 0, very small area, and we will write it as ds, and in place of summation we will replace it with close integral. Okay, so summation we can use, delta S we can use when surface area we are taking small elements. Okay, although but these small elements also have some significant surface area. Okay, but if we are taking very small, negligibly small surface area, then this delta S will be tends to 0, and it will be denoted by ds, and this summation will convert to close integral. Okay, so where Q is the electric charge enclosed by the surface. Okay, so Gauss law for electrostatic indicates that electric monopoles or isolated charges exist. Okay, for electrostatic it is not equal to 0. That means electric monopoles exist. But Gauss law for magnetism is also B dot close integral B dot ds is always 0. That means magnetic monopoles do not exist. Since magnetic field lines form closed loop, there are no sources or sinks of magnetic field. That means we cannot define the originating point of the magnetic field. It is always in the form of closed loops. Okay, so we cannot determine that it is originating from north or south. Got it? The simplest magnetic element is a dipole or current loop. All magnetic phenomena can be explained in the terms of arrangements of dipoles and current loops. Thus, Gauss law for magnetism is, so final statement, the net magnetic flux through any closed surface is 0. This is a statement for Gauss law for magnetism. Is the concluded statement for the Gauss law for magnetism, that is the net magnetic flux through any closed surface is 0. Okay, now we will do example 5.3. So many of the diagrams given in figure 5.6 show magnetic field lines, thick lines in the figure wrongly. Okay, so in diagram 5.6, many arrangement or pattern of magnetic field lines are shown wrongly. So point out what is wrong with them, and some of them may describe electrostatic field lines correctly. So some of them may be correct, or some of them may be describing electrostatic field correct, but not magnetic field. Okay, so there are magnetic field lines are being shown. Okay, but some of the cases are there where magnetic field lines are shown wrongly, but it can be true if we replace magnetic field lines with electric field lines. Okay, so some of them may describe electrostatic field lines correctly, but not magnetic field lines. Point out which ones. Okay, so this is the diagram. A, B, C, D, E, F, G. 7 diagrams are there. 7 patterns of magnetic fields are there. So you have to determine whether magnetic field line pattern is correct for this given orientation, given configuration or not. Or either it is correct for electrostatic field. Got it? So let's do the solution. So A part is wrong. This configuration, magnetic field lines for this configuration is wrong. This is the straight conductor carrying current in the upward direction. It is shown. This is a straight conductor and it is carrying current in the upward direction. Magnetic field lines are in this pattern around a straight conductor carrying current. In what pattern magnetic field lines are there around a straight conductor? Write in the comment section. What pattern of magnetic field lines are there around the straight current carrying conductor? So figure 5.6a, magnetic field lines can never originate from a point like shown in the figure. Okay, so magnetic field lines cannot originate like that. Okay, so it should be concentric circles. Okay, circles can, okay, so it cannot originate from a point like that. These field lines are better represented by electrostatic field. Okay, so magnetic field lines can never originate because they form continuous closed curves. Okay, over any closed surface, the net magnetic flux must always be zero. That means inward flux will be equal to the outward flux. Okay, so if we consider any closed surface over there, there will be only outward flux. So it will violate the Gauss law for magnetism. Okay, that means this pattern of magnetic field lines is incorrect. So inward flux will be equal to outward flux. Field lines shown represent electric field. The field lines that are being shown in this 5.6a figure is electric field lines of a positively charged wire if charge is static. If this is a linear charge, this is a wire containing a static linear charge. So this is the pattern of electric field lines due to a wire carrying static charge. Okay, this is not the representation of magnetic field lines. Magnetic field lines around a current carrying conductor is in the form of concentric circles around the wire or conductor in the form of closed loops. So this is incorrect pattern. Correct magnetic field lines are in the form of concentric circles around the current carrying straight conductor, and it is in the form of this. So this is a conductor carrying current in this direction, and this is the pattern of magnetic field lines. Figure showing correct pattern of magnetic field lines. Okay, so that pattern is incorrect, and that is better representing the electrostatic field for a conductor or any insulator carrying static charge. B part is B diagram. The diagram shown in B part is also wrong. So this is a figure 5.6b. Okay, so what is wrong there? Okay, you can answer me in comment section before I answer. Okay, so I can see that how many of you have understood the concept. Okay, this is figure 5.6b. So what is wrong in this diagram? Why it is not representing the magnetic field lines? Okay, so you can see there are two types of magnetic field lines. Yes, first one is magnetic field lines do not cross each other. These magnetic field lines are crossing each other. That means they are incorrect pattern. This is incorrect pattern. Second wrong thing, there is a closed loop of magnetic field lines. But according to Ampere's circuital law, if there is a closed loop, so BDL, closed integral BDL should be equal to mu naught I, means that closed loops must contain some current passing across them. So there is no current passing across them. So how these closed curves are there without any current? Okay, so two things are wrong. First one is they cannot cross each other. Okay, let's see. As we studied, magnetic field lines like electric field lines can never cross each other. Otherwise, the direction of field at a point of intersection is not unique. Secondly, there is further error in the figure from the Ampere circuital law. Close integral B vector dot dl vector is equal to mu naught I. Okay, so means close integral along this closed loop. Okay, magnetic field along close integral of magnetic field along the closed path will be equal to mu naught I. Means these loops should contain some current across them, but there is no current across them. This is 0. That means BDL should be also 0. But here is closed loops. So this is error in the diagram also. Okay, if B dot DL is non-zero, this is non-zero because it is being shown magnetic field lines in the closed loops existing in the region. So it is non-zero. Then I enclosed through loop taken has to be non-zero. So I enclosed should be there, but there is no I enclosed shown in the figure. So there is an error in the figure also. In other words, closed loop of static magnetic field, static magnetic line must enclose a region across which current is passing. Okay, that closed loop that is being shown in the diagram, they must enclose a region across which current is passing. Hence, static magnetic field can never form closed loop around empty space. Okay, so magnetic field lines cannot form closed loop around the empty space where there is no current. So given figure is wrong. Even electrostatic field lines can never form closed loops, neither in empty space nor when the loop encloses a charge. So electrostatic fields can never form closed loop for any condition. But magnetic field lines can form closed loops, and they form closed loops when there is a current in the region. If there is a current, then around that current they form closed loops. But if there is no current, they cannot form closed loops. Got it? C part of this diagram is right. Why right? This is a form of toroid. That dotted blue part is the windings. Okay, I have mentioned how toroid is formed. There is a solenoid. We have to hold both the ends of the solenoid, and after bending the solenoid, we will touch both ends of the solenoid after bending it in the form of a circular configuration like this. Okay, so this is the windings. These blue dotted lines are windings, and both the ends are connected below. Okay, due to which the formed configuration is now toroid. This is toroid. And we know that magnetic field lines outside the solenoid is nearly zero or weak. Okay, so only magnetic field lines will exist inside the core of the solenoid. Now we have bent the solenoid in the form of toroid. So magnetic field lines will be in the form of this circles, concentric circles. But these magnetic field lines only exist in between the windings, not outside the windings. Okay, so this is the right representation of magnetic field lines for a toroid. So magnetic field lines are completely confined within a toroid. So these magnetic field lines will be confined within the windings of the toroid, not outside. Outside magnetic fields are zero. Okay, so nothing is wrong here in field lines forming closed loops. Since each loop encloses a region, so each loop is enclosing a region. So these windings are having current. All the windings of the toroid is having current. So this loop, innermost loop, is enclosing some amount of current that is flowing through these windings. Okay, outer windings is enclosing more amount of current. Other outer winding is enclosing more amount of current. Okay, so nothing is wrong here in the field lines forming closed loops, since each loop encloses a region across which a current passes. Okay, now we have discussed in our one lecture in our one question in our previous or yesterday's lecture that is it possible that any pole do not exist? Okay, we know that monopoles do not exist, but is it possible that both of the poles do not exist? So that the answer was for a toroid and for a straight infinite conductor. Now you can see for a toroid, magnetic field lines are in the form of closed loops. Can you determine what is the north pole and what is south pole here? No, you cannot determine, because magnetic field lines are closed loops. There is no end and there is no point of origination. There is no point of ending. Okay, so we cannot determine the poles in the toroid and for a straight infinite conductor. So nothing is wrong here in fields line forming closed loops, since each loop encloses a region across which current passes. For clarity of figure, only a few field lines within the toroid have been shown. Only a few lines have been shown. There are number of lines, field lines in the space confined in the toroid. Okay, actually the entire region enclosed by the windings contain magnetic field. D part of this figure is also wrong. Why wrong? You can see this is a solenoid. This is the windings of solenoid and magnetic field lines are shown in that pattern. Is it the correct pattern for a solenoid? What is wrong in this pattern? You can tell me. Okay, is it correct pattern for the solenoid? What is wrong in this pattern? So we know that for a long solenoid, magnetic field is parallel to the axis and uniform inside. For a long solenoid, if the solenoid is finite, not very long, okay, so the magnetic field line near the center is uniform and along the axis, but near the ends, it is non-uniform. The pattern resembles the bar magnet pattern. Okay, that means field lines due to a solenoid at its ends and outside cannot be completely straight. Inside or near the center, it can be straight and parallel to the along the axis, but at ends, it cannot be completely straight and confined. Such a thing violates Ampere's law. Okay, if we are taking loop here near the center, it will enclose some current and show the magnetic field line, show the value of magnetic field. If we are taking this same loop, half of the loop is out in the outward side of the end, half of the loop is on the right side of the end. Okay, so now current that is the loop is enclosing the current half of the amount as compared to the previous case. Previous case, if this loop is, if I am taking Amperian loop at the center and it is confining in between three windings. Okay, it is covering three windings or enclosing the three windings of current. Okay, but now I am placing this same Amperian loop of same area. I am placing it at the end such that it is only enclosing two windings and one small part of this loop is outward in the direction outward at the end. Okay, means it is only enclosing two windings. In simpler terms, it is only enclosing the two windings. Okay, now magnetic field is same. In this pattern, magnetic field is shown same at the end and at the center, both. So magnetic field will be giving the value same. So BDL will give the same value, but current enclosed is different now. Okay, so it will violate the Ampere's law. That is BDL is equal to mu naught I. So I, the amount of current enclosed has changed, but magnetic field is same according to this pattern. That is wrong. Okay, so it will violate the Ampere's law. Line should curve out at both ends and meet eventually to form the closed loop. Correct pattern of field lines for a solenoid is shown below. So that is the correct pattern. So it should be, the field lines are continuous and straight and parallel to the axis near the center, and near the end the magnetic field is non-uniform. Okay, so these field lines will spread like that. They will bend and bend to form the closed loops outside like this. Got it? So E part of this is correct. This is the pattern of magnetic field for a bar magnet. Figure 5.6 E. Okay, is it correct? It is correct, because at the center of this bar magnet, the magnetic field lines are parallel to the axis and confined within and straight. At the ends, magnetic field lines are bending and magnetic field is non-uniform, and they are forming closed loop outside. So this is the correct pattern for a bar magnet. So these are magnetic field lines outside and inside a bar magnet. Field lines are forming closed loop, which is correct. And also at the ends, these field lines are also bending and appear to form a closed loop. Okay. Now F part of this question is wrong. So this is the field lines. So these are not representing magnetic field lines, because if this part, this shaded part is some magnetic dipole. Okay. So magnetic dipole, we know that monopoles do not exist. So this element should contain both north and south pole. Okay. So if magnetic field lines are exiting from one of the side, then from other side, magnetic field line should enter. But magnetic field lines are exiting from both the ends. Okay. If we are considering one Gaussian surface around it, around this shaded plate. Okay, so magnetic flux will be non-zero, because all the magnetic field lines are exiting. So there will be net outward flux, which will violate the Gauss law for magnetism. So these field lines, the direction of field lines is wrong. Look at the upper region, all the field lines seem to originate out, okay, of the shaded plate. Consider a closed surface enclosing the upper shaded plate and region around it. Net flux through that surface is not zero. Okay, because there is all the magnetic field lines are originating out. So there will be outward flux, and this is impossible for a magnetic field. Okay, because for magnetic field, magnetic flux through any enclosed surface must be zero. Okay, so what are these field lines? These are resembling the electrostatic field, not magnetic field. Okay, so it is representing the electric field or electrostatic field, considering this plate is positive and this plate is negative. So due to this positive plate, all the electric field lines are originating out, exiting this plate, and this negative plate, all the electric field lines are entering this plate. Okay, so these given field lines in this pattern in fact show the electrostatic field lines around a positively charged upper plate and a negatively charged lower plate. These are not showing the magnetic field lines. And the last part, G, is also wrong. Why? This is a north pole, this is a south pole, and these are magnetic field lines from north to south is shown. Okay, they are so confined and straight from north to south, which is not possible. There is a fringing. There can be fringing of the magnetic field lines at the ends. So figure 5.6G, magnetic field lines between two pole species cannot be precisely straight at the ends. So we cannot say it is similar to solenoid. At the ends of the pole or at the ends of solenoid, magnetic field lines are not completely straight. There may be fringing like that. Magnetic field line will originate from north. Okay, it cannot originate, but for this region we are considering, it will start from north and it will bend like that. It will be some like bended magnetic field line, not straight. At the ends it should be bended. So they are not cannot be precisely straight at the ends. Okay, some fringing of lines is unavoidable. We cannot avoid the effect of fringing at the ends. Ampere law is violated. This is also true for electric field lines. Okay, electric fringing is always there. Okay, fringing we have also studied in capacitors. We have taken the large area of the plates of capacitor, or we have decreased the separation between them so that fringing effect can be avoided. At the ends of these plates, the the electric field lines between the plates will not be straight line. It will be bent. It will be bent line. Okay, that is called fringing. So we cannot avoid the effect of fringing. Either it is a special case. Okay, so fringing is unavoidable. Okay, now came to summary. Magnetic field lines are always closed loop, unlike electric field lines, which can start and end on charges. There are no magnetic monopoles. Magnetic field lines cannot emerge from or terminate at a point. Gauss law in magnetism states that the net magnetic flux through any closed surface is zero. That is closed integral B vector dot dA vector equal to 0. Magnetic flux phi is defined as the product of magnetic field strength B and the area A perpendicular to the field lines. That is phi equal to BA cos theta, where theta is the angle between magnetic field direction and normal to the surface. It represents the total magnetic field lines passing through a given surface area normally. Okay, so there are some practice questions. What is Gauss law for magnetism? Why is it different from Gauss law for electric fields? Okay. Second question, why can't we have isolated magnetic monopoles? Support your answer with a simple diagram. And another question, compare magnetic field lines and electric field lines. Okay, so what are the similarities and difference? Got it? So thank you, but DPP section. First question, which of the following statement is true regarding Gauss law for magnetism? The net magnetic flux through a closed surface is proportional to the enclosed magnetic charge. The net magnetic flux through a closed surface is always zero. Magnetic field lines can originate from a single point in space. Or magnetic monopoles are required for Gauss law to hold. So you can comment your answer A, B, C or D. Which diagram correctly represents the magnetic field lines? Field lines crossing each other, field lines forming closed loop around a straight current carrying conductor, field lines emanating, that means originating from a single point, field lines completely straight at the ends of the solenoid. If magnetic monopoles existed, how would Gauss law for magnetism be modified? If monopoles existed, if we are taking any condition that monopoles exist, if we are taking imaginary situation, then Gauss law for magnetism will be modified for, according to analogous with electrostatics, it would be which statement about magnetic field lines and moving charge particle is correct? Magnetic field lines represent a path moving charge will follow. The force on a moving charge is always tangent to the magnetic field line. Magnetic field lines indicate the direction of force on a moving charge. The force on a moving charge is perpendicular to magnetic field lines. Can a system have a magnetic moment even with zero net charge? No, magnetic moments require net charge, or if current system has current loops with no net charge, only if magnetic monopoles are present. No, charge is necessary for magnetic effects. So all answers are correct. Got it? Okay, thank you. I hope you enjoyed the session.